Hello all, and welcome to this next session of the course Pre-MBA Statistics. So now, as you might know, that we're sitting in the last week here and roughly 2 more sessions to go before we end this short little course on Pre-MBA Statistics. Now again, if you vaguely remember, what we discussed in the last couple of sessions, or rather last 3 sessions in this week, was broadly focusing on regression analysis or linear modeling or least squares regression and so on and so forth. And particularly, just to give you a very quick sort of a refresher, so that all the things we'll discuss today and the next session would be sort of in line, is that we focus more on SLR. So firstly, what do you mean by SLR? So SLR stands for simple linear regression, and again, simple linear regression means you have a single x and obviously a single y. Okay. Now again, just a small point of clarification, that even if you extend SLR to MLR, which is called as multiple linear regression, there would still be a single y, which is a single response variable that you would like to predict down the line, but there would be more than one, or rather more than one independent variables or more than one x variables there. Okay. But again, extension from SLR to MLR is not very difficult. So you have to sort of build up a linear structure there also. And probably, if time permits, in the problem session we'll take up a couple of examples related to MLR, that is in the last session of this week. Okay. Now again, we have discussed so far that how do you sort of develop the linear model, then how do you sort of estimate the parameters, namely beta 0 and beta 1, and then we discussed the interpretation of the slope parameter and the intercept parameter. So again, if we sort of discuss very briefly, that beta naught hat happens to be nothing but B0, while beta 1 hat happens to be B1. So B1 measures the slope of the linear structure, while B0 measures the intercept of the linear structure. And then in the last couple of sessions, we discussed the interpretation of B0, B1 in a particular context of a practical example. Okay. And then, if you vaguely remember, the last session we sort of discussed more about sum of squares. So SSR, SSE, SST, and so on and so forth. So again, if you remember the scatter plot, the skin cancer mortality rate, if you take a random point on the scatter plot, then you sort of are able to break down the overall distance into 2 parts, right? And then from there you get this nice little equation, which is SST equals SSR plus SSE. So here SSE stands for residual sum of squares or error sum of squares, SSR stands for regression sum of squares, while SST stands for the overall variance that you have in the model or total sum of squares. Okay. And now, just before we move ahead with the analysis of variance that you see in front of you on this slide as a heading, I'd again like to sort of go back to this equation and then probably spend very few sort of minutes, not really minutes, but a short duration on sort of explaining that what's going on in this equation that you see here. Okay. So firstly, the moment you talk about sum of squares, okay, so firstly, any sum of squares are kind of related to some variance component. Okay. So you should understand this very critical point, that when you talk about sum of squares, by the formula of sum of squares or by the nature of any sum of squares, be it SSR, SSE or SST, sum of square entity itself is kind of similar to some variance component. Okay. And again, if you vaguely remember, in the last session we discussed the idea of capital R square, which is coefficient of determination, and there, while explaining the idea of capital R square, we had the exact same definition, that the amount of variation explained by the regression model out of the total variance. And again, if you remember the formula of R square, you simply divide SSR by SST. Alright, so again, all these sum of square components in themselves are nothing but some sort of a variance components to begin with. Okay. Alright, so now the next idea that we'll talk about is again very important. It's called as analysis of variance. I'm very sure you might have heard about this term number of times, or if not the bigger version, you might have heard about ANOVA. Alright, so ANOVA is nothing but analysis of variance. So the full form of ANOVA is analysis of variance, and analysis of variance is a sort of a key hypothesis testing procedure when it comes to regression or when it comes to multiple comparisons and so on and so forth. Okay. And here we'll make use of the exact sum of squares idea, because again at the end of the day you are trying to analyze the variance components and not the mean components. Okay. So at any time point, if you want to analyze the variance components, again like I said, the variance components are somewhat in line with the sum of squares we discussed earlier, be it a short while back or in the last session, namely SSR, SSE and SST. Okay. So this session will devote some time on sort of explaining that how do you structure the ANOVA, then how do you sort of quantify different variance inside ANOVA, and so on and so forth. Okay. So again, the first slide is sort of a refresher that we've discussed all these sum of squares, SSR, SSE, SST, right? And again, like I said, even in the last session, that the SST is somewhat similar to variance in your response. Okay. Of course, you don't divide it by 1 by n minus 1 here, but the structure of the sum of squares or rather total sum of squares is similar to any variance among the y variable component. Okay. And again, one very important point here to note is that, so if SSR is large, it suggests significant association between x and y. Okay. And if SSR is a large component, naturally your R square would also be close to 1, because R square is nothing but SSR by SST. Okay. So when you construct that ratio SSR by SST, if the SSR component itself is a large component, it will suggest that you have a significant association between x and y, your fit is good, and so on and so forth. Okay. Now just a digression, in the last session towards the end, if you remember, we discussed a t-test as well, right? And where my beta naught or rather h naught was beta 1 equals 0. So let me write down the null hypothesis. It was beta 1 equals 0, while the alternative was beta 1 is not equal to 0, isn't it? And under SLR or simple linear regression, if you want to sort of quantify more formally through a hypothesis test whether you have a significant relationship between x and y, this is the way to go. Okay, so simply construct a t-test where these are the hypotheses, you test it out, you either find out the p-value or the critical value, then you compare and then come to a conclusion. Okay. And here we will sort of extend the idea of a t-test to a ANOVA, and using what? So through the idea of sum of squares. Okay. So you will see very soon that what I am trying to tell you, but again, so I guess this slide is more of a refresher of sum of squares and what would happen if SSR is a large component in that ratio. Okay. Now again, this second slide itself is nothing new, just a small refresher so that you're not disconnected entirely. So again, you have the standard example of skin cancer mortality rates, and there, like I said, if you pick up a random observation yi and try to quantify the total distance, I can sort of split the entire distance between yi and y bar into two parts, and this exactly gives rise to this nice little equation there. Alright, now one step ahead, once we sort of formulate the equation you saw on the last slide, then the next idea is that each of those sum of squares has some degrees of freedom. Okay. Now again, the term degrees of freedom is not new to you. So again, when we talked about hypothesis testing, let's say t-test or chi-square test or f-test, etc., etc. So each of these distributions have certain degrees of freedom. So for example, even in the last session we talked about a t-test where you're sort of testing beta 1 equals 0 and beta 1 not 0. Again, there the distribution of the test statistic was a t distribution with n minus 1 degrees of freedom, okay, or rather n minus 2 degrees of freedom. My bad. Okay. But now we'll try to understand that how many degrees of freedom are there for each of the sum of squares that you saw on the last slide. Okay. So again, naturally n minus 1 degrees of freedom are there for SST. So for the first component of the LHS, which sort of gives you the total sum of squares, you have n minus 1 degrees of freedom. For the residual sum of squares or error sum of squares that you have in between the equation, you have n minus 2 as the degrees of freedom. And for the third component, which is the remainder, which is SSR or regression sum of squares, you have a single degree of freedom or 1 degree of freedom. Okay. So especially under SLR, you should remember all these 3 degrees of freedom. So n minus 1 for SST, n minus 2 for SSE, and 1 for SSR. Now a couple of points here to mention that this 1 also stands for how many x's you have in the model. So again, if you remember, we are talking about SLR where you only have 1 x. Okay, and hence the degrees of freedom for SSR becomes 1. So if you extend SLR to MLR, let's say having 2 x's, then degrees of freedom for SSR would be 2, 3, 4, etc. Okay, and similarly, as we had an equation on the last slide, similarly we can sort of formulate this equation as well, which has to be quite intuitive because degrees of freedom should also add up. Okay, so df for SST is on the LHS n minus 1 equals df for SSE, which are n minus 2, plus df for SSR, which is simply 1. Okay. Now of course, why do you require degrees of freedom? Of course, when we construct the test statistic of ANOVA, we have to sort of divide the sum of squares by the corresponding degrees of freedom there. Okay. Alright, so a simple sample ANOVA table. So again the same example, skin cancer mortality rate, and again note that the sample size or number of observations are 49 here. Now again before we sort of delve into some mathematics, just to try to tell you that how exactly an ANOVA table looks like. Okay, and by the way, all these outputs are from the R software. So again, if you are not very comfortable with R, that's perfectly fine. But again, just to tell you that if you are sort of into R, or if you have worked with R before, you can sort of try testing these on your end. Okay, so again, let's say if you fit the model in that skin cancer mortality rate example, then this is exactly how the ANOVA table should look like. And essentially this is exactly what the ANOVA table looks like in the middle that you see. So again, you have two components there. First one is X, second one are the residuals, and then you have several columns in that table. So the first column gives you degrees of freedom, and again make sure that they are matching. So again, if n is 49, there should be n minus 2 df for the residual component, which is 47, and 1 df for the SSR component, which you see here. So by the way, this X stands for the regression and residual stand for SSE. And then the next column gives you the sum of squares. So the first one, 36464, are nothing but SSR. So SSR is 36464, while my SSE is 17173. Alright, and if you simply add these up, you should get SST there. Okay. Now the third column is also important to us, which is called as mean square component. So again, how do you get mean square? So mean square is nothing but you simply divide the sum of squares, the corresponding sum of squares, by the degrees of freedom. So SSR divided by 1 would give you MSR, while SSE by n minus 2 would give you MSE. And we've already discussed MSE a couple of sessions back when we tried to estimate the variance. Okay. So again, if you're not very comfortable, you can go back to that video and then try to see that one more time. But then the mean square components are nothing but you simply divide the sum of squares by the corresponding degrees of freedom there. And lastly, the test statistic value, which is kind of more important to us, is this F value. So by the way, this entire ANOVA revolves around a F test. So the underlying distribution of the test statistic is an F distribution. Okay, and how do you arrive at that F distribution? We'll see very soon. So essentially, what we are doing is we are sort of dividing MSR by MSE there. Okay, so if you form this formulation or this small ratio, it should yield the F value there. And lastly, P value. Okay. Now so before we move ahead, one simple conclusion that if you simply observe the P value of the underlying ANOVA, what can you conclude? So you can pause the video and try to answer the question. So again, here the particular ANOVA is giving a very small P value. Okay. So if you have a very small P value, you will be rejecting the null. Okay. Now again, remember one thing, that we're again through this ANOVA, we're kind of again testing the significance between X and Y. So we're kind of pinpointing the same hypotheses, whether beta 1 is 0 or beta 1 is not 0, or more formally in English, we are sort of testing whether there is a significant linear relationship between X and Y. Okay. So let's say you run the ANOVA, you get the P value, and if P value is very small, less than alpha, which is let's say 5% or even 1% here, then the conclusion would be to reject the null, which means that there is a significant relationship between X and Y. Okay. So again, like I said, understanding the P value from an ANOVA is kind of exactly similar to how you do it for any other hypothesis test. Okay. Alright, now how do you exactly get hold of that F test value, right? So in the last table, you must have seen the F value 99 point something. So how do you arrive at that value? Okay. So again, like I said, this is just a formulation of both the mean squared components, so MSE and MSR. So in order to get the mean squared component in ANOVA, I simply divide the sum of squares by the corresponding degrees of freedom, as discussed a short while back. Okay. Now we'll do one small tweak here. So we'll try to find out the expected mean square values. Okay. So we'll try to find out on one hand expectation of MSR, and then we'll try to find out expectation of MSE as well. Okay. So again, we'll not get into details, but one can actually prove mathematically that expectation of MSR component that you saw on the last slide happens to be all of this. So slightly mathematical, but then one can actually solve it mathematically and then try to prove that. Okay. On the other hand, expectation of MSE is exactly sigma square. We discussed this a couple of sessions back, like I said, right? And there we've discussed that MSE is an unbiased estimator of the variance. So expectation of MSE has to be sigma square. Okay. And again, like I said, just to press upon the fact that what exactly are we testing here? We're testing the exact same hypothesis, whether beta 1 is 0 or beta 1 is not 0 there. Okay. Now one small point before we move ahead, obviously it's written down the next slide, but again, So think of a situation that what we are trying to test here. We are trying to test whether beta 1 is 0 or beta 1 is not 0. Okay. So again for a second assume that beta 1 is 0. Okay. So again just for a second assume that beta 1 is 0, which means that H naught is true. Okay. So again go back to these two sort of formulations and then try to sort of tell me or try to answer that what would happen if beta 1 is 0. So again you can pause the video and try to answer. So the answer to this simple question is that if beta 1 is 0, so where do you see beta 1 here? You see beta 1 right here. Okay. So if this beta 1 is 0, this entire component would be 0, and then both the expected value of MSR and MSE would be equal to sigma square. Whereas if beta 1 is not 0, this MSR would be more than MSE, or rather expectation of MSR would be more than expectation of MSE. Okay. So I can sort of tabulate a simple thing. If my beta 1 happens to be indeed 0, in that situation my MSR by MSE ratio should be close to 1, because this entire component like we discussed earlier would be 0, and then you will end up the ratio would be sigma square by sigma square, which is close to 1. So firstly I will try to write down expected value so that there is no confusion. Of course, so expected value of MSR by expectation of MSE should be close to 1, whereas if beta 1 is not 0, expectation of MSR divided by expectation of MSE would be bigger than 1. Okay. So this is a very simple conclusion one can draw based on whether beta 1 is 0 or beta 1 is not 0. Okay. So essentially speaking, we can actually take the test statistic for an ANOVA to be essentially MSR by MSE, because this is exactly what we want to test for. Okay. Now of course we can leave aside the expected values because the test statistic has to be some sampling quantity. Alright. So MSR is a sampling quantity which contains not, I mean of course the parameters, but also the sample values, and on the other hand the denominator should be MSE. So are you with me when I say that using this ratio we should be able to tell whether beta 1 is 0 or beta 1 is not 0. So whenever beta 1 is 0, this ratio should be close to 1. Whenever beta 1 is not 0, this ratio should be significantly away from 1, or rather greater than 1. Alright. And this is exactly what's given in the next slide. So rather than reading from the slide, I thought that I'll try to explain that very briefly to you before we sort of delve into the conclusion. So again, if beta 1 is 0, just to summarize, the ratio MSR by MSE should be 1. If beta 1 is not 0, the ratio MSR by MSE should be bigger than 1. Thus, MSR by MSE, this ratio can be used as a test statistic to test out the hypotheses concerned with ANOVA there. Alright. Now again coming back to the exact same table without any numerical values and a practical sort of a example, but then again this is a standard table which we have seen on the couple of slides back as well. So again regression component, error component, total component, then the next column gives you sum of squares, SSR, SSE, SST, then you have the DFs 1, n minus 2, n minus 1, then the mean square component, MSR, MSE, and finally the expected value of the mean square components there. And this sort of boils down to the final version, which is F test for beta 1. So again if you remember, we are sort of testing the same hypotheses whether beta 1 is 0 or beta 1 is not 0. Our test statistic here, interestingly MSR by MSE, follows a F distribution. Okay. And why an F distribution? Because again, how do you derive an F distribution? So F distribution is a ratio of two chi-squares divided by their degrees of freedom. So it so turns out that SSR and SSE are both chi-square variables. Okay. And hence this ratio MSR by MSE turns out to be an F distributed variable. Okay. So again then you can sort of go ahead very naturally how we do for any other test, you find out the null distribution. So in this case this actually follows an F distribution with 1 comma n minus 2 degrees of freedom. And then the critical value, and then the final conclusion that you reject the null if the absolute value of the test statistic exceeds the critical value, or you can sort of find out the p value and then conclude the test from the p value also. Okay. Now very interestingly, under SLR only, if you focus on a simple linear regression setting, then an F test and a t test which we saw in the last session are equivalent. Okay. So on one hand if you give me the p value corresponding to a single t test, on the other hand if you give me the p value corresponding to an ANOVA or an F test for an SLR situation only, then both those p values should be exactly identical. And this is exactly what we see here. So under SLR, I guess it's the same example, skin cancer mortality rate, and then this ANOVA table we've seen before a few slides back, and then simply focus on the p values. So the top version gives you ANOVA, The bottom version gives you the summary of the fit, which is nothing but the t-test. Okay. So, on one hand you have this p-value, on the other hand you have this p-value that you see here from a t-test, and they are almost, not almost, they are exactly identical. Okay. Hence, this is a very sort of an interesting point, or more like a lemma you can call it, that f-test and a t-test, or rather ANOVA and a t-test should give you the exact same results under SLR only. Of course, if you extend SLR to MLR, of course things would be different, because there will be more than one X's and so on and so forth. Alright, so I guess we are kind of done with ANOVA, and now what next? Now what next? Okay, so let's say you've created the model, you've sort of tested either using a t-test or ANOVA, right? Now the next important step that you have to do, if you remember vaguely, we've been discussing number of times about, let's say, diagnostic checking. Okay, diagnostic checking for linear regression, or alternatively it's called as residual analysis. Now again, if you vaguely remember, a couple of sessions back we talked about line conditions. So again, what are they? So again, you can pause the video and then try to think that what do you mean by LINE. So line conditions are nothing but 4 assumptions about the regression model. So linearity, independence, normality and equal variance. Okay. Now once you sort of formulate the regression model, you are kind of okay with the estimates, you are kind of okay with the ANOVA conclusion or the t-test conclusion, right? Then you sort of have to sort of ensure that the 4 assumptions are being met by the regression model or not. Even if at least one of the assumption is not met, you have to sort of correct it slightly and then move ahead, okay, before you sort of put forward the final conclusion. Okay. So how do you do it? So this entire idea is called as diagnostic checking, like I said, or residual analysis, and you can sort of do this entire exercise using number of plots. We will sort of discuss one very easy plot called as residual versus fit plot. Okay. So you have a simple scatter plot, you have 2 axes, x axis and y axis, and then this plot is residual versus fit. So it's nothing but EI versus YI hat. EI stands for residual values, YI minus YI hat, and on the other hand fit means YI hat values, or the fitted Y, or the fitted response values. Okay. And essentially if you draw this residual versus fit plot, it should show a random scatter of points around the 0 line. Okay. It should actually show a random scatter of points around the 0 line. We will see an example very soon. And this residual versus fit plot is actually used to detect non-linearity, unequal variance and outliers. Okay. So only these problems. So if you create a residual versus fit plot for any practical example, it can sort of tell you a lot of things about, let's say, linearity or other non-linearity, and the other problem it sort of focuses on is unequal variance. So of course 2 more problems we are left with, normality and independence. Okay. Alright, so I'll give you a simple example, again the standard example, skin cancer mortality rate. By the way, this is nothing but the scatter plot that we have here initially. Okay. And here a couple of conclusions is that the points are kind of tight around the red line, so the fit might be good. And again, if you remember, long back we discussed the capital R square value for this guy. It was around 67% or 0.67, which is quite decent. Okay. Now let's see how the residual versus fit plot looks like for the same example. Okay. So let's say once you fit the, so firstly how do you construct this plot? So let's say once you create the regression model, you get hold of these 2 entities, so EI and YI hat from the regression model, or rather the regression model fit. Okay. And then like I said, on the y axis you keep the residuals, on the x axis you keep the fitted values. Okay. And then you simply create a scatter plot between the residual values and the fitted values. Okay. Now remember, there is an assumption that summation EI so summation EI is close to 0. Okay. And again we discussed this number of times even before, that there would be some error points above the line, there would be some error points below the line. So summation EI is roughly close to 0, and this is exactly what you see in the scatter plot here. Okay. So this horizontal line that we have drawn at 0 sort of denotes this property here. Okay. So if you are plotting residual versus fitted values in the scatter plot, all the points should be randomly scattered around that horizontal 0 line. Okay. And if it happens to be true, then we say that linearity assumption is met and equal variance assumption is met. Okay. And again through this plot you can clearly see that there is not a major problem. So you have all the points scattered randomly, some are above the 0 line, some are below the 0 line, and again you do not see any pattern here per se. Okay. So the key point to note here is that there should not be any significant pattern in the residual versus fit plot that should be evident to you. Okay. If you have random scatter of points around that horizontal 0 line, then you are good to go. Okay. So, we have sort of check marked the non-linearity assumption or rather linearity assumption and equal variance assumption through the residual versus fit plot. Okay. We will take another small example. So, let us say we will sort of highlight the problem of non-linearity here. So, this one is an interesting data set. So, it says that is tire tread wear linearly related to mileage. Okay. So, you have a small example and then on the x axis you have mileage, on the y axis you have groove, which is called as a tire tread wear, okay, or rather depth of remaining groove, and then this is just a scatter plot to begin with, and then you can see that the red line is doing a good job, but then you have a small curvature here, right. A small quadratic model or some sort of a non-linear model will be slightly better. So, linearity might be a problem. So, how do you check it? Okay. So, again like I said, you create that residual versus fit plot, and then here you can starkly see that it is in fact a curve that you see here. So, points are not randomly aligned along the 0 line, right. So, they are sort of decreasing then increasing. So, you see a clear U shape here, which is a problem. So, linearity is a problem in the example we saw. Okay. So, this is exactly how the points should actually scream at you whether, or rather this plot should actually scream at you whether you have some problems or not really. Okay. And now the last step. So, how should you go ahead? So, let us say if you have some problems, if linearity is a problem or equal variance is a problem. So, of course, we have not discussed normality and independence yet, again due to paucity of time, but then the key aspects are more on linearity side. I mean, if the relationship itself is not linear, then there is a starking problem to begin with. Okay. And of course, the variance should also be consistent. So, both those problems are kind of sort of verified using the residual versus fit plot. Okay. Alright, but now the last slide is to what should you do if you do have some problems. So, again the last slide we saw the groove versus mileage example where you had a non-linearity problem, then what? Okay. Then the solution is you have to transform. So, transformation. So, again what do you transform? You transform either x, you transform either the y variable or you transform both. Okay. So, small comment that if at least one of the line conditions is not satisfied, if you at least have one problem out of the 4 problems, suitable transformations are required on the variables. Okay. So, now you have 3 categories. When should you transform only x? So, you should transform only x when non-linearity is the only problem. When should you transform only y? So, you should transform only y when normality is a problem or unequal variance is a problem, etc., etc. And when should you transform both x and y when you have mixed sort of problems or all problems. So, non-linearity is also a problem, normality is also a problem, etc., etc. So, you should transform both x and y. And these are some standard transformations that people apply. So, log, square root, inverse and many more. Okay. So, when you say log, essentially what you are doing is simply taking a log of let us say either x variable or log of let us say y variable that you have. You make a transformation, you refit the regression in a hope that the problem would be solved there. Okay. Alright, so just to sort of summarize in this session, we talked about number of important points, ANOVA, how do you construct the F test, how F test is similar to T test, and then once you do it, you have to sort of ensure that the 4 assumptions are being met through residual analysis. We only talked about one very standard plot called as residual versus fit plot, and of course, if you have some problem in the example, you should go a step ahead and then involve some transformations to be applied on the variables in hope to correct the problems that you have. Okay. Thank you.